Hello. Today we're going to cover what is called matrix review, but may actually not be a review at all for you. But it is the information that we need to know in order to go into the last chapter that we cover in this course. The last chapter is called we use the eigenvalue problem in order to solve a system of differential equations. But before we can even talk about an eigenvalue problem, we have to be able to talk about systems in matrices and what matrices are and how to work with them, all the things. Okay, so we're going to start kind of from scratch, and I would say rather quickly go through some of the basic properties of matrices and how to work with them, how to solve a system with them, and then we'll get into the eigenvalue problem for just a standard system not related to differential equations. We'll wait for that until we get into chapter 8. Okay, so most of the topics are just going to be covered by an example to illustrate the process. Of course, in our book in Appendix B, there is a lot of information for you to read through and many examples as well. The first thing we need to talk about is the size of a matrix. When we refer to a matrix, we talk about rows by columns, the number of rows by the number of columns, and that's what gives it its size. And so rows are the horizontal things and columns are the vertical things. And so if we have m rows and n columns, we say that its size is m by n. An m by 1 column vector is a matrix with m rows and 1 column. And that's why we have to have this consistency of naming the size as a rows by columns thing so that we can, talk about them and understand what each of us is talking about. A 1 by n row matrix is a matrix with 1 row and n columns. If the number of rows and columns are equal, then we call that matrix a square matrix. Okay, another topic is the addition and scalar non-matrix scalar multiplication. Okay, we can't talk about multiplication until we're done talking about the linearity properties of matrices. So addition requires that matrices have to be the same size. That way we can add like components and subtract like components. If we had two matrices that were of different sizes, there may be like an extra component that doesn't get combined. Scalar multiplication, scaling, it just means to stretch or shrink. So it's just a multiplier. But scalar multiplication requires a sort of distribution of the scalar number to all components of the matrix. So we're going to simplify this next row here, this next line here, to just one matrix. Here we have the 5 times the matrix that has components -1, 3, 13, and 8. Notice the way I read the matrix was the first row items and then the second row items. Then we'll do -4 times the matrix that has components 1, -3, -7, and 6. So what we do is we first distribute the 5 and we distribute the -4 into each of the matrices. But it's not just going to go to one component. It has to go to all 4 components, each of them. So when I distribute the 5 through, I end up with a new matrix whose components are -1 times 5, which is -5. 5 times 3 is going to give us 15. 5 times 13 is going to be 50 plus 15 was 65. 5 times 8 is 40. And then plus, and then I'm going to distribute the -4. I like to distribute the minus signs because then it takes care of any double negatives, and then I can do the rest of the math kind of in my head. So when I distribute the -4, I get -4 times 1 is -4. -4 times -3 is 12. -4 times -7 is positive 28. -4 times 6 is -24. Now I combine like components. So if it's in the first row, first column, it has to go with the first row, first column in the next matrix. So that means my first row, first column will be -5 minus 4. My first row, second column will be 15 plus 12. Second row, first column is 65 plus 28. Second row, second column is 40 minus 24. One more simplification and we're done. We get -9, 27, It's going to be 8593. And 40 minus 24 is 16. So the linear combination of those two matrices that we started with is going to give us this final 2 by 2 matrix. So adding and subtracting matrices should not change the size. It should remain the same size. All it's going to change is the components that are inside of the matrix. The next topic to talk about is the multiplication of matrices. This one's kind of weird. Multiplication of matrices is not a commutative matrix or operation. So if I have two matrices, A and B, AB is not necessarily equal to BA. So order absolutely matters. The other thing is that one order may be possible while the other order is impossible. Okay? In a product, we are going to take each column of the second matrix and multiply them with each of the rows of the first matrix. This requires that the number of columns of the first matrix must be the same as the number of rows of the second matrix. I just want to talk about that really, really quick with regards to the A and the B that are down here. Okay, so in A, it looks like the number of rows by the number of columns here. So A is a 3 rows, so it's 3 by 2 columns, whereas B has 2 rows by 3 columns. So A is 3 by 2 and B is 2 by 3. So when it says that the number of columns of the first matrix, so for us that's 2 in matrix A, must be the same as the number of rows of the second matrix, which is 2 for B as well. That's the only way we know that we're going to actually be able to multiply. And so this one will work. And then it says we're going to take the column of the second matrix. So for us, that would be this first column of B. And then we're going to multiply that with each of the rows of A. And what I mean by multiplying, it's like you can picture the first column of B, lift it off and turn it on its side so it's horizontal, and then multiply with the like components in each of the rows of A. And I'll show you how that looks in just a moment, but let's finish going through this paragraph. The multiplication is component-wise, and then those products will be added, and the result will be a new component in the resulting matrix. So if I'm taking the first row of A times the first column of B, that product in addition should give me the first row, first column of AB. Okay? So essentially, if we're looking at the first row and the first column of the resulting matrix, the product comes from the first row, the first matrix, and the first column of the second matrix. If we look at the second row and third column component of the resulting matrix, this came from the product of the second row in the first matrix and third column in the second matrix. This is much easier to see in an example, so let's go ahead and work through this. In this one, we already know the sizes are good. Okay, so we're going to do the multiplication. We've got 1, -5, -3, 2, 4, 9 times -4, 6, -3, 1, -3, 2. All right, so the result, when we do the multiplication, the resultant matrix will be equal to the outer dimensions of each of the matrices. So the outer dimensions are 3 and 3, so our resultant should be 3 by 3 matrix. Remember, the inner dimensions need to be equal for the multiplication to happen. The outer dimensions tell us the size of the result. Okay, so let's go ahead and first examine when we take the first column of B times the rows of A. So we have to picture that -4, 1 being put on its side, made it get horizontal, and multiply with each of the rows. So I'll have a 1 times a -4 plus -5 times 1. Okay, that's the first row of A times the first column of B. Now that first column of B needs to go to the second row. So we get -3 times -4 plus 2 times 1. That'll give me the second row of the first column in our resultant. Then we take the first row times, or sorry, the first column of B times the third row of A. That'll give us 4 times negative 4 plus 9 times 1. And then once we're done sending the first column of B through all the rows of A, we are done with the first column of the resultant matrix. Then we can move on to the second column of B to get the second column of the resultant matrix. So we're going to take that 6, negative 3, and we're going to turn it on its side so it's horizontal, and we're going to multiply it with each of the rows of A. So we get 1 times 6 minus 5 times negative 3. We get negative 3 times 6 plus 2 times negative 3. We get 4 times 6 plus 9 times negative 3. And that takes care of the second column of our resultant matrix. Then we move on to the third column of B and send it through the rows of A in order to get our third column for our resultant. So that will be 1 times negative 3 minus 5 times 2. It will be negative 3 times negative 3 plus 2 times 2. And then we'll have 4 times negative 3 plus 9 times 2. Then we figure out what all of those products and sums are, and we have our result. So going down the columns, in the first row I get negative 4 minus 5 is negative 9. Then I get 12 plus 2 is 14. I get negative 16 plus 9 is, what is negative 16 plus 9? This is hard to do. That's going to be a negative 7. And I get 6 plus 15 is 21. I'm in my second column now. Negative 18 minus 6 is negative 24. And then 24 minus 27 is negative 3. And then my second column is done. Moving to the third column. Negative 3 minus 10 is minus 13. 9 plus 4 is 13. Negative 12 plus 18 will give me 6. And this is AB. That is my resultant matrix. Okay, so it's a little bit weird. You may have to do this a few times just to get comfortable with it. And there are examples in the book to also work with. Okay, I'm not expecting that my one example is enough to be the be all end all. I do have an expectation that you will go through the examples in the book to really make sure that you're firm on these topics. Okay, the next topic is finding the derivative or the integral of a matrix. It's done component by component, and the good thing is derivatives and integrals are not new for us. We know how to handle this. So the only weird thing is that we have to be able to remember that if we're taking a derivative of a matrix, we deal with each of the components, and the same for the integral. So first we'll look at the derivative, dA dt. dA dt says that we're going to go inside of the matrix and we're going to take d dt of each of the components. So d dt of 1 over t squared plus 1 in the first row, first component, or sorry, first row, first column, then d dt of 3t in the first row, second column, d dt of t e to the 2t in the second row, first column, and d dt of cosine of pi t in the second row, second column. So we go ahead and take those derivatives. I'm not going to focus so much on how to take a derivative because this section is about matrices, and the derivatives hopefully are old hat. Just, verbalizing it, I would rewrite the 1 over t squared plus 1 as t squared plus 1 raised to the minus 1, and then use a power rule and the chain rule on there to get a negative 2t over t squared plus 1 quantity squared. Derivative of 3t is just 3. The derivative of t e to the 2t requires a product rule, and it'll give us e to the 2t plus 2t e to the 2t. And the derivative of cosine of pi t is 8. We're going to get a chain rule there. Move my 3 over. And that'll give us the negative pi sine of pi t. And that's it. If we want to integrate a dt, then that means we have to, in a way, distribute the integral to each of the components inside. So instead we look at the integral of 1 over t squared plus 1 dt, the integral of 3t dt, the integral of t e to the 2t dt, and the integral of cosine of pi t dt. So the antiderivative of 1 over t squared plus 1, that's an arctan of t. Remember, that's one that you just kind of have to know. The antiderivative of 3t will give me a 3/2 t squared. The antiderivative of t e to the 2t after an integration by parts, where we use u is t and dv is e to the 2t, so that du is dt and v is 1/2 e to the 2t. Using the integration by parts, this is going to give us a t over 2 e to the 2t minus a 1/4 e to the 2t. And the antiderivative of cosine of pi t will give us a 1 over pi sine of pi t. And that's it. Okay, so nothing too different. Mostly it's just annoying because if you're told to take a derivative, it's not just one, it's 4 derivatives here. And if it was a bigger matrix, then it'd be even more derivatives. And same with the integrals. All right, the next topic is solving a system of equations using matrices. So in solving a system using matrices, there are elementary row operations that are allowed to be used. We're allowed to multiply a row by a non-zero constant, mostly because that is the same as if we had an equation, we could multiply both sides of the equation by a constant, and that wouldn't change the result. Okay. We are allowed to interchange any 2 rows, and that's because if we have a system of equations, we're allowed to rewrite them in any order that we want. And we're allowed to add a non-zero constant multiple of one row to any other row. And that amounts to the same thing as taking 2 equations and adding the like sides in order to eliminate a variable, which is usually why we're doing it. These are the only row operations allowed to be used. There are no others. Don't make any up. We use them to get our matrix into what we call a row echelon form or a reduced row echelon form. We're going to focus mostly on the row echelon form. And what has to be true for that is that the first non-zero entry in a non-zero row is a 1. In consecutive non-zero rows, the first entry 1 in the lower row appears to the right of the first one in the higher row. Rows consisting of all zeros are typically at the bottom of the matrix, although there are some times where we don't want them there. And if we want to go to reduced row echelon form, we have one additional criteria. A column containing a first entry of 1 has zeros everywhere else. So let's see how we can apply this to the following system of equations. We're given 3 equations, x plus y minus 2z is 14, 2x minus y plus z is 0, and 6x plus 3y plus 4z is equal to 1. These are all planes. Like you could think of, if you're sitting in a room right now, you could think of the 2 walls and the ceiling. Those are all flat planes, and they meet at the corner. And so we're trying to find what the x, y, z values are for that corner where they all intersect. It's not always true that they intersect in one point. If it was 3 walls that all intersect in a line, that would be different, okay? But we won't know until we solve the system. So to solve the system, I first rewrite it in the form of a matrix, okay? And a matrix is only going to care about the coefficients, but the matrix is very orderly. It cares where you put things. So the first column will always be for the x's. The second column will always be for the y's. And the third column will always be for the z's. And then in our case, the fourth column will always be for the constants on the other side of the equal sign. So when I write out my matrix, my first row has the coefficients of x's. So I have 1, 2, and 6. The second column has the coefficients of the y's. So I have 1, minus 1, and 3. The third column has the coefficients of the z's. So minus 2, 1, and 4. Then I do an equal bar. That gives my eyes something to notice Like that's my equal bar. So variable coefficients are on the left, and on the right are the constants that were on the other side of the equal sign. So I have 14, 0, and 1. Okay. Now, if I was just working with equations, my first step would be to try to use equation 1, the x's that are in equation 1, to eliminate all the x's that are in equations 2 and 3. Okay, so I'm going to do that with the matrices. Now remember, I'm allowed to take my row and multiply it by any number as long as I send that number through the entire row. And then I could add it to another row. So here's what I'm going to do. I'm noticing that the coefficient of x in the first row is 1. If it was a -2, I could combine it with the second row and I would eliminate the x's. So I'm going to see about, what if we do -2 times row 1 plus row 2? Then that's going to equal the new row 2. I'm going to write out what that means, okay? So, and this is all just with numbers, no variables. This is where you're going to have to get used to things. So if I send a -2 through row 1, my coefficients are now going to be a -2, a -2, a 4, and a -28. Then I write the coefficients out for row 2. And those are no different than they are in the matrix. It's just 2, -1, 1, and 0. Then I add them component-wise. -2 plus 2 is 0. -2 minus 1 is -3. 4 plus 1 is 5. -28 plus 0 is -28. This is my new row 2. So when I write out my matrix the next time, I have the same row 1 as before, 1, 1, -2, 14. But row 2 is now 0, -3, 5, -28. Row 3 remains the same, 6, 3, 4, 1. Put your equal bar in, and now we have our new matrix. So all I did was eliminate x in the second equation when I did this. Now I want to eliminate the x's in the third equation. If the first column in the first row was a -6, I could add it to the third row, and that would get rid of the x's. So it seems like -6 is the multiplier I need to send through row 1, and then add to row 3 to give me a new row 3. So when I multiply row 1 by -6, the coefficients I get are -6, -6, 12, 14 times 6, that's going to give me a -84. My row 3 remains the same, 6, 3, 4, and 1. I add my components and I get 0, -3, 16, and -83. So this is my new row 3. So when I write out my matrix, now rows 1 and 2 stay the same. 1, 1, -2, 14 for row 1, 0, -3, 5, -28 for row 2, and row 3 is now 0, -3, 16, -83. And so now what we can see is that the first column looks beautiful, 1, 0, 0. That is getting the first column into row echelon form. Okay, so if I have a 1 in row 1, then in column 1, then I should have zeros below it, and I do. Next, I move on to the second row. Second row, second column. I want to use that now to eliminate below it. So if I'm in the second column, I'm dealing with y's, right? So I have -3 y's in the second row. If that was a +3 and I added it to row 3, I would get rid of the y's in row 3. So let's do that. I need to make row 2 the negative of what it is. So I do a -1, row 2, plus row 3. This is going to give me a new row 3 that has the y's eliminated. So the coefficients of row 2, when I send a -1 through it, they will be 0, 3, -5, 28. The components of row 3 are 0, -3, 16, and -83. When I add my components, I get 0, 0, 11, and 55, -55. Okay, so that is my new row 3. So I write out my matrix again. I have 1, 1, -2, 14, 0, -3, 5, -28. And my new row 3 is 0, 0, 11, -55. Okay, now at this point, this is almost in row echelon form. Technically, in row echelon form, the diagonal, all the elements would be 1s. And so I could take one more step, but it's okay. You know, we can solve it from here. We've made this so much easier on ourselves. So row 3, what it's telling me is 11z is equal to -55. That means that z is equal to -5. So that's why I felt like I could stop, because row 3 is going to tell me what z is equal to. Row 2 is saying -3y plus 5z is equal to -28. But I can plug in z equals -5. I have -3y plus 5 times -5 is equal to -28. And so then -3y, I'm going to add 25 to the other side. It's equal to -3, so y is 1. Okay, that's great. Well, I can take that and I can deal with row 1 now. Row 1 says x plus y minus 2z is equal to 14, but replace z with -5 and y with 1. X plus 1 minus 2 times -5 is equal to 14. -2 times -5 is positive 10, so I have x plus 11 is 14. X is equal to 3. And so what I found here is that x, y, z, the ordered triplet, is equal to the point 3, 1, -5. So that's where the three walls are intersecting in one point. Okay. All right, so that's how we solve a system. Of course, every system is going to bring up different nuances. And so you want to solve several if you've never done this before. This is technically a college algebra level problem that we're working with, but I don't want to assume that everybody covered this in their algebra class. So this is the review. But again, there's more content on this in the book, as well as more problems to practice in the homework and in the book. The next topic is the eigenvalue problem. Okay, I told you this would be really fast. We're like diving deep and doing it all at once. So the eigenvalue problem, I'm going to kind of just read what I've written here because I've really put some time into how to say this the best way. The textbook definition of the eigenvalue problem says that a number lambda is just a constant, is said to be an eigenvalue of a matrix A if there exists a non-zero solution vector k of the linear system A times k equals lambda k. So what's happening here is the matrix A multiplies with the vector k, and the result is a multiple of k, because lambda is just a number, right? So that's kind of a special k vector, because when a matrix A multiplies with any random vector, you won't necessarily get back just a multiple of that random vector. You'll get something completely different. Here's what else it's saying. Vectors point in a specific direction in space. This k vector, when it gets multiplied by A, it doesn't change its direction. It changes its length, but not its direction, because the components of it will be the same up to a constant multiple. So the solution vector k is said to be an eigenvector corresponding to the eigenvalue lambda. We typically find lambda first, and then once we know lambda, we can use it to find our k vector, the eigenvector. So here's, I've already talked about this just a little bit, but here it is written. If you have a matrix A and a vector k, and you multiply them as A times k, then the matrix acts on the vector by changing its magnitude, that's how long it is, and its direction. A matrix will act on some vectors by only changing their magnitude, but leaving their direction unchanged, or maybe just reversing it by 180 degrees. Vectors such as this are called the eigenvectors of the matrix. A matrix acts on an eigenvector by multiplying its magnitude by a factor, lambda. This factor lambda is called the eigenvalue associated with the eigenvector. Because eigenvectors are special vectors for a matrix, we wish to find any that belong to a matrix. Now, the equation AK equals lambda k is called the eigenvalue equation, or problem. Let's see what we can get by performing some algebra on it and treating it like a regular old equation that we need to solve. So back in algebra, we were always told, bring everything to one side of the equal sign and leave 0 on the right-hand side. So if I subtract the lambda k over, then AK minus lambda k is equal to 0. That 0 is a 0 vector, by the way. I have it bolded. Normally vectors would have little hats on it, but it would look like this, okay? Any vector k can be written as I times k, where I is the identity matrix of the same size as A. Here's I. Let's, for example, a 3 by 3 would be 1, 0, 0, 0, 1, 0, 0, 0, 1. So it has ones on the diagonal and zeros everywhere else, okay? And I is like the identity in multiplication in matrices, because if you take it, just like the number 1, if you take I or if you take 1 and you multiply them by something, you get the something back. So I times k is just k. Note that an identity matrix has all ones on the left to right downward diagonal and zeros elsewhere. Okay, so I'm going to rewrite from the equation up above. We are rewriting the k as ik here. That's the only difference from the previous step. Once we've done that, then we can factor the k that's common to both terms. But when we factor it, we have to be careful because it is multiplied on the right, which means it needs to factor out on the right. Multiplication is not commutative with matrices, so do not factor that out on the left. Okay? So here's our factored form. Now we need a non-trivial solution to the above equation. And since, k equals 0 would be trivial, we don't want that as our solution. That's kind of the boring solution. And so now we're going to need a little bit of theory to deal with this. A homogeneous system of n linear equations, so homogeneous meaning that this is equal to 0, homogeneous system of n linear equations in n unknowns has a non-trivial solution if and only if the determinant of the coefficient matrix is 0. Okay, so the coefficient matrix for us is going to be this A minus lambda I. So to find a non-zero solution for k, we have to solve the following. The determinant of A minus lambda I has to be equal to 0. That will allow us to find the lambda values that we need. This is called the characteristic equation of A. And the roots of this equation are the eigenvalues of the matrix A. Once we know these, we can find the corresponding eigenvectors. And the best way to see what all this means and how to do it is for us to just do it. So that's what I'm going to do. We're supposed to find the eigenvalues and eigenvectors of this matrix A that has components 1, 6, 0, 0, 2, 1, and 0, 1, 2. So the first thing that we do is that we're going to solve the determinant of a minus lambda I equals 0 for lambda. Okay, so the determinant of a minus lambda I is in the straight up and down bars. Our components, we look at, remember lambda I, I should write this out. So we have, let's see, determinant of A, which is 1, 6, 0, 0, 2, 1, 0, 1, 2, minus lambda I. Well, I just has the lambdas on, or the ones on the diagonal, so that's where our lambdas show up. We get lambda 0, 0, 0, lambda 0, 0, 0, lambda. Okay, so we want the determinant of this, which means that we are looking at the determinant of 1 minus lambda, 0, 0, and then we have 0, 2 minus lambda, and then 1, and then we have 0, 1, and 2 minus lambda. Okay, so that's what we want to take the determinant of. And I'm going to break this up into the pieces. So it's a 3 by 3. I need to deal with the rewriting of this. Remember our signs and everything. So I'm going to take that first component in the first row, first column, and I have equals that 1 minus lambda times the determinant. If we were to remove the row and column that 1 minus lambda is in, we would then be looking at the 2 by 2 determinant of 2 minus lambda, 1, 1, 2 minus lambda. So this part's not new. We've dealt with determinants. Then we have minus 0. And I'll just write it out, but 0 times anything is 0. But the components inside of the 2 by 2 would be 0, 1, 0, 2 minus lambda. And then we have plus the third piece, so plus 0. And removing the column and row it's in would give us a 2 by 2 of 0, 2 minus lambda, 0, 1. Okay, and this is equal to the 1 minus lambda times, now in that 2 by 2, I need to do that diagonal product, so I have 2 minus lambda times 2 minus lambda minus 1 times 1. And then minus 0 and plus 0. And all of this needs to equal 0. So we're forcing it to be 0. Now, I need to multiply and distribute. So first, I'm going to leave the 1 minus lambda distributed out because that's what I should do. It's already factored. Don't distribute it. Our goal is to factor. And if you already have something that's fully factored out, save yourself some agony by not multiplying it back through. We're going to deal with what's inside the brackets. Okay, so when I multiply those out, I get lambda squared minus 4 lambda plus 4 minus 1. And so I have 1 minus lambda, and then inside here, lambda squared minus 4 lambda plus 3. And that factors a little bit more, so we have 1 minus lambda times, it looks like lambda minus 3, lambda minus 1 equals 0. So when I set each of these equal to 0, this gives me lambda is equal to 1 twice, and lambda is equal to 3. I'm going to deal with the lambda is equal to 3 first. So for lambda, I'll call it lambda 1 is 3. We have to solve a minus 3i set equal to 0. And where is that coming from? Let's go up here. It's coming from right here. This equation, a minus lambda I times k equals 0, we're solving that equation for k. Okay? And this notation that I'm using right here in, I've got, it's the parentheses around it, so that's like in the matrix, a minus 3i equals 0. We're going to solve this for k1. So that's going to be our first eigenvector. Okay, so I have this written down, so I'll just write it down here. So we're solving this matrix. We have a minus 3i will give us 1 minus 3, 6, 0, and then it's set equal to 0. Second row, 0, 2 minus 3, 1, 0. Third row, 0, 1, 2 minus 3, 0. Put the equal bar in. Okay, now let's rewrite this so it looks better. Take care of those subtractions. We have minus 2, 6, 0, 0. We have 0, minus 1, 1, 0. And we have 0, 1, minus 1, 0. If I was to take row 2 and add it to row 3, I could get a new row 3. And because I don't have to do anything to it, I don't really need to show a whole lot here. I can see what I've got. Row 2 plus row 3 equals the new row 3. Row 1 stays the same, negative 2, 6, 0, 0. Row 2 stays the same, 0, negative 1, 1, 0. But if I look back at the previous iteration, if I combine rows 2 and 3, I get 0, and then negative 1 plus 1 is 0, 1 minus 1 is 0, and 0 plus 0 is 0. So what I got was a row of zeros. Let's translate what this says, okay? The first row, row 1, well, actually, I'm going to start with row 3. Row 3 is saying that, and remember, we're solving for a k vector, so the third component of a k vector, we'll call it k3. K3, or I should say 0 times k3 is 0. That's what a row of zeros is saying. And that's mostly because I have elements in the other diagonal parts, okay? 0 times k3 equals 0. What that means is that k3 can be anything. So I'll just say k3 equals k3, right? We can pick any number. I could say k3 is equal to c, okay? Row 2, what that's saying is negative k2 plus k3 is 0, or in other words, k2 is equal to k3. But k3 is equal to c, so k2 is equal to c as well. Row 1 is saying negative 2k1 plus 6k2 is equal to 0. So negative 2k1 is equal to negative 6k2. k1 is equal to 3k2, but k2 is equal to c, so this is 3c. So my eigenvector, my k1 eigenvector, is equal to the vector that has components k1, k2, and k3, but we just found that each of those can be written in terms of c. So it'll be k1 is 3c, k2 is c, k3 is c. I can factor out the c, and I leave behind what's important, 3, 1, 1. Whatever the c is doesn't matter a whole lot, okay, because it could be anything. All right, next is for lambda 2 is equal to 1, we're going to solve the a minus 1i set equal to 0 for k2, and we'll see what ends up happening. So I've got a repeat on my eigenvalue. That's a suspicious sort of thing, and it should be suspicious. It may give us one eigenvector. It may give us two eigenvectors. Hard to say until we actually just do the math. Okay. So again, I've got it written down here, so I'll just write it. If we look at a minus 1i, the components are 1 minus 1, 6, 0, 0. And then second row, 0, 2 minus 1, 1, 0. Third row is 0, 1, 2 minus 1, and 0. Put the equal bar in. Let's rewrite things a little bit nicer. First row is 0, 6, 0, 0. Second row is 0, 1, 1, 0. Third row is 0, 1, 1, 0. Okay, now I can use the negative of row 2 and add it to row 3, and that will clear below. I'll get my new row 3. Row 1 stays the same, 0, 6, 0, 0. Row 2 stays the same, 0, 1, 1, 0. But if I take a negative of row 2 and combine it with row 3 is now gone. We expect there to be a row of zeros when we're finding eigenvectors. That's kind of the whole point. We want a non-trivial solution, but everything is set equal to 0. So we need to get something where like one of K1, K2, or K3 is just kind of free. It gets to be whatever we want it to be, and we let it be some C value. That has to happen in order for us to get eigenvectors. Okay, now I'm looking at this, and I'm looking at how, like, where my pivots are, and what I'm seeing in my diagonal elements. I used a word that you don't know. I used the word pivot, and I'm sorry about that. Pivots are the items that are along the diagonal, and I only have one thing on the diagonal, that 1, 1. However, if I were to move my rows around a little bit, let's see, because I'm allowed to move the order of equations. And I want to do this because I think it's important for you as a student to see, like, how do we handle this? I don't have a pivot for column 1. Or, I don't have a 1 in column 1. In column 2, I've got 2 things. In column 3, I've got 1 thing. I'm going to move row 2 to row 3. I'm going to switch them. So I'm going to take row 2 and swap it with row 3. Row 1 stays 0, 6, 0, 0. Row 2 is now 0, 0, 0, 0. Row 3 is now 0, 1, 1, 0. And I chose to do that because now I have a number in the diagonal there. I have that 1. But I'm looking at this, I'm like, in the first row, there's a 6 in the second column. If the non-zero item is in the second column, then it should be in the second row. So I'm going to swap row 1 and row 2. And what ends up happening is row 1 now has zeros, 0, 0, 0, 0. Row 2 is 0, 6, 0, 0. Row 3 is 0, 1, 1, 0. Okay, so now what I can see is a better view of what my diagonal elements should be. So sometimes we have to rewrite things so we can actually see what's going on here. Row 3 is saying K2 plus K3 is equal to 0. So that means K2 is equal to minus K3. That's all I got from there. Row 2 is saying 6K2 is equal to 0, which means K2 is equal to 0. Row 1 isn't saying a whole lot. It might be pretty confusing for you. But I already have information about K3. Like there's a 1 in the K3 position in row 3. But in row 1, I have nothing for K1. So what I have in row 1 is 0K1 is equal to 0. That means that K1 can be anything we want it to be. K1 or C. But with K2 equal to 0, that means K3 is equal to 0. Because K3 is equal to a negative of K2. So what I get for my eigenvector for lambda 2 is equal to 1, the eigenvector associated with that eigenvalue is K2. It has components K1, K2, and K3. K1 is equal to C. K2 is 0, K3 is 0. I can factor out the C, and I leave behind the important part, 1, 0, 0. So this is the eigenvector that is associated with lambda 2 is equal to 1. So just to summarize, For lambda 1 equals 3, we have k1 eigenvector is equal to, what did we get, 311? I'm only taking the important parts. The c in there isn't very important. And then for lambda 2 is equal to 1, we have k2 eigenvector is equal to a vector with components 1, 0, 0. And that's all I have. The eigenvalue problem is very, very new. Even if you've seen matrices before, this is very new. Definitely work through several problems. When we get to section 8.2, so we're going to take a break from this in 8.1, but when we get to 8.2, we're going to then expand upon this and see how we can use the eigenvalue problem to solve differential equations. As always, if you have any questions at all about the material, please reach out.